Hello, everyone. Thank you for attending today's webcast on lab and simulated performance of heat pump water heaters with thermal storage, UEF, and first hour. I'm Harvey Sachs, a visiting fellow at HWF, and I'll be the moderator for this session. We'll start with a few housekeeping announcements, then quickly move on to the presentation. First, thank you to all of our sponsors and HWF ally members for their support, the Hot Water Forum and HWF. Next, please check out all the tabs on the left-hand side of the app. From there, you can network with attendees and program participants, visit sponsor pages, and engage in our game to possibly win a free registration. And there are other sections as well that you can explore. Unfortunately, because this session is being recorded prior to the start of the Hot Water Forum, we will not have the opportunity to answer questions. However, we encourage you to reach out to the speakers with any questions or information you have to share. They can be reached by messaging them in the Program Participants tab on the left-hand side of your page, or by reaching out to them by email. The presenters have either shared their email on their slides or they'll include it in their presentations. Now I'd like to introduce our distinguished speakers. They're Joseph Rendell, Oak Ridge National Laboratory, First Hour Rating Improvements, and Jian Sun, Oak Ridge National Laboratory, on model-based co-simulation of heat pump water heater with phase change materials. We'll start with our first speaker, Dr. Joe Rendell. He was the first graduate of the Texas A&M Kingsville with a PhD in Sustainable Energy Systems Engineering. Joe studied flow distribution in stratified hot water tanks at Oak Ridge. He also invented a self-priming hand pump that plumbers could use to siphon water out of a tank, and is the lead inventor on a patent dip tube for increased extraction efficiency and first hour rating. He'll discuss laboratory experiments using embedded thermal storage materials to improve UEF and first hour ratings. Thank you. Joe?
Thank you for the introduction, Harvey. I'll be presenting the results of an alpha prototype heat pump water heater with embedded thermal energy storage. The research team includes Oak Ridge National Lab, A.O. Smith Corporation, and Will Smith, who now works with Gas Technology Institute. In this presentation, I will show how thermal energy storage materials can increase the first hour rating of water heaters, and how the alpha prototype has been the best-in-class ratio of first hour rating to the nominal heating capacity of water heater technologies for tanks between 50 and 60 gallons. Critical to realizing this benefit was selecting the material, determining the amount of material to use, determining the encapsulation method, and the deployment strategy of the materials, constructing the prototype, and finally testing the prototype. I will quickly go over the benefits of heat pump water heaters, the goals and benefits that we came up with this prototype, down selection of how we down selected the materials, and the development of the alpha prototype, finally concluding the work with the benefits. So heat pump water heaters can reduce energy consumption and CO2 dramatically. The 4 quads per year of energy are consumed in water heating, and the heat pump water heater is a great solution for this. Although when the electric resistance elements turn on due to a large water draw, sometimes the benefits aren't as good. So we've studied mostly hybrid heat pump water heaters, but as we went through the development, we figured out some potential impacts for other technologies and system design. So our goal was to increase the efficiency and deployment of heat pump water heaters while reducing the carbon footprint and enable demand response programs to save users money. The secondary benefits that we came up with is that the smaller tank could be used to reduce the stacking effect of too hot of water when approaching the smaller tank, which I'll describe in the future slides. Also for gas tankless water heaters that have the cold sandwich, and in any situation where you have a long line and you're getting cold water when you don't expect it. To begin with, we did a literature and patent review of different types of materials that we split into phase change materials and thermochemical materials. The list here shows where the current research is and the state of the art. You can see that the system configurations for the PCM materials has been researched more recently, and model and experimental projects have been just about equal. With TCM materials, the material research itself increased dramatically recently, and it sort of equates to the material being more at the bench scale than in system analysis, although that there are some studies in system configurations. To down select the materials, we set up a criteria of 6 different categories. We looked at the temperature first, the storage density, the cost, the compatibility, the heat transfer characteristics, and are these materials produced at scale? Within those 6 criteria, there's 2 major ways of installing PCM or TCM with heat pump water heaters. One, you can go inside the tank or outside of the tank. For going inside of the tank, due to FDA requirements, there's only a few select items or a few materials that can work. Food grade paraffins and soy wax are 2 that we identified as good candidates. For outside the tank, Rubitherm 8 to 15 or Rubitherm 40 to 65 for in the evaporator or in conjunction with the condenser, depending on, you will have different temperature ranges. Also, sodium acetate trihydrate seems like an interesting material as well. Unfortunately, none of the heating powers from the thermochemical materials had enough capacity for heat pump water heating unless we switched from a standard heat pump water heater to some type of sorption system. So the concept behind our deployment is pretty novel. We developed some IP with the team members to focus on 2 major concepts or 2 major improvements. First, we wanted the PCM to be able to float above the tank where it doesn't interact with the outlet water. You'll see that this tank is stratified, and after a while, slightly less hot water will approach the outlet, and the PCM spheres were designed to be neutrally buoyant at this point, where they would then be hotter than the water and giving temperature out to increase the amount of hot water you would get out of the outlet. Thirdly, the stratified tank would at some point discharge all of the PCM, and it was designed to float then below the level of the outlet or the hot water that we desire. And then finally, the 4th stage, the PCM is recharged and floats again to the top. On the right-hand side, you can see one example of a neutrally buoyant PCM sphere. To construct these PCM spheres, or capsules as we're calling them, 2 major improvements were found for the heat transfer. One, there was an external metal fin, which has a conductivity of 1,000 times greater than the PCM itself. And internally, there was also a coiled fin that, while having the same high conductivity, also increases the surface area for heat transfer. The construction of the PCM capsules required a fair amount of effort and somewhat of an extended process. We melted the PCM, vacuum infused it, inserted the coil, and had to seal the PCM spheres. In total, we made about 1,300 capsules that were tested in 2 different tanks, or 2 different test runs, one with about 942 spheres and the other one with the full amount. To test these actual spheres in an experimental apparatus, we constructed a system described on the left here, where there's a larger 50-gallon tank and then a smaller 6-gallon tank where we deployed the PCM spheres. We had many different measurements for temperature, power, pressure, and of course, a flow meter. We also had a differential pressure across the evaporator, and in total, we logged about 80 channels of data to characterize how this new heat pump was working. This was tested in one of many Oak Ridge Beatrick chambers, and you can see the lab view screen gives us a heads-up display of all the different things going on that we're measuring during a first hour rating test. Today, I'm going to talk about a 1D model we created to predict the performance of this system just briefly, but we also did a 3D finite element model to create visualization of the flow pattern and to create a specialized dip tube to ensure a lot of mixing in the secondary tank, smaller tank. The 1D model was used to size the amount of PCM spheres to put into the tank to ensure that the outlet temperature didn't decrease 15 degrees Fahrenheit below the set point per the requirements of the first hour rating. And the amount of PCM that could be fully discharged or utilized over the complete first hour rating test was optimized. You can see in these two graphs that the prediction of when the first draw stopped was very similar to what we actually measured in the first draw of the first hour rating. On the right-hand side, you can see the 3 different draws of a full FHR. This graph depicts what's happening inside the PCM itself. So first, the PCM in the secondary tank will get charged, and that is shown as a negative utilization of the PCM because energy is going into the PCM. And then after some time, the temperature will drop below the level of the PCM or the freezing temperature, and heat will be given from the PCM back to the water to a positive utilization number. This happens each time over the 3 draws. The conclusion is, for their first attempt, the PCM amount was appropriate, and we were able to utilize 77% of the energy stored in the PCM by assuming a well-mixed tank and using experimental data to calculate these values. Finally, the results you've been waiting for. Shown here is the alpha prototype compared to typical in-class hot water heaters. There's a gas electric, a typical electric heat pump water heater, and then the baseline electric heat pump water heater, which was one we were developing for a different purpose, but was suited well for the testing that we did. So, excuse me, overall, we saw a 30% increase in our baseline in first hour rating when using the alpha prototype. This was an apple-to-apple comparison, and the first hour rating achieved was 79 gallons. Shown is also the nominal storage capacity of the different water heaters. On the y-axis of this graph, I've plotted first hour rating over nominal heating power, where for the conventional gas storage, I've converted BTUs per hour to watts. So you can see the conventional systems all have lower first hour rating to the power that they put in. So what we want is hot water in the first hour rating, and what we don't want to spend is the heating power to get to that hot water point. So you can see that the conventional storage systems don't perform as well, although our baseline units did somewhat well. Our flex heat pump water heater, which is our alpha prototype, did the best, and it did the best when 208 volts was used, single phase, instead of 240 volts. So in conclusion, some PCM materials are ready for deployment in hot water tanks. Deployment will increase user satisfaction and allow for more demand control by utilities. Hotter storage temperatures can be accommodated with PCM materials as well. Ongoing work will bring an embedded solution to the market soon, and encapsulation optimization for passive control and heat transfer are undergoing in our beta design. Systems designs are being considered for larger applications, and I've hinted at some of those potential secondary benefits already. Thank you, and please send any questions or follow-up to me, Kashif, or Jin.
Thank you, Joe. Our second speaker is Jian Sun, a research scientist at ORNL. He has diverse engineering experience and expertise in thermodynamic system design, modeling, control, and optimization. Before joining ORNL in 2019, he was with UTC Carrier Corporation, leading development of model-based design and data analytics methods and integrating them in HVAC&R product design and controls development. John will present his Oak Ridge work, and here he is.
Okay.
Thank you.
Thank you, Harvey. Thank you for the introduction. And thanks to have the opportunity to present our work. The topic I would like to present today is a mode-based co-summation of a heat pump water heater with phase change material thermal energy storage. So what we would like to cover today, the first one, we will give some introduction and background information on the heat pump water heater with the phase change material thermal energy storage. After that, we will go to the detailed description on how we model the heat pump water heater with the phase change material thermal energy storage. In the final, we will present some submission results and use this core submission platform based on the model we developed. So the concept of the new system design is to add phase change material thermal energy storage capability into the standard heat pump water heat. The motivation of this new system design is to increase the heat pump water heater storage and delivered capacity, also increase the flexibility to enable demand response. The additional storage capacity will allow for large amount of peak shifting without sacrificing the quality of the hot water delivered to the customer. The system diagram in the right side shows a small external tank connected with the top of the standard water tank. This is just one of the configuration we used for experimental purpose. The actual product may put the phase change material inside of the tank, normally will be on the top of the tank. So as we will know, both steady state submission and dynamic submission has been widely used in the HVAC industry to support products development for decades. In general, the steady state submission focuses on the system mass, energy, and moment balance of an equilibrium state. It is based on the high fidelity component model. It is suitable for system and component design. The dynamic submission studies the system transient response and is generally used for control development. It usually does not require the rigorous component model because of two reasons. One is that the commonly used control in the HVAC industry is feedback PID control. The control performance evaluation does not require high fidelity system model. Secondly, high the high-fidelity dynamic model significantly increases the number of equations and variables and creates tremendous challenge for the master solver. So in this case, a hybrid approach will be used, which we combine the steady-state equipment model with the dynamic tank simulation. The water tank and the phase change material thermal energy storage tank will be simulated with the dynamic modeling to reduce the computational cost. A one-dimensional dynamic model is used. In each control volume, the temperature, pressure are assumed to be uniform. Compared to the water tank and the phase change material thermal energy storage tank, the heat pump system experiences much faster transient response to a change and can be represented with a steady-state model. In this slide, we show a dynamic model for the water tank based on the conservation law of the mass, energy, and momentum balance. For simplification, a few assumptions are used. The first one is internal velocity and force over the temperature of the tank are negligible, so the dynamic of the momentum is not required. Also, during the small temperature operation range, normally it's from 55 degrees C to 95 degrees C, there is no phase change in water, so the mass balance is a steady state. Based on that, only energy balance is considered to be dynamic in this model. Another important assumption is that the enthalpy profile from inlet to outlet of the refrigeration coil is a quadratic function. This slide shows the phase change material thermal energy storage model. The thermal energy storage tank is designed as a 6 to 10 gallon water tank, 6 gallon tank with phase changing material inside. For simplification, all this phase changing material can be considered to be equivalent to a phase changing material cylinder placed inside the tank with water flowing over the surface. Similar like water heater tank, the dynamics of the phase change material thermal energy storage tank are mainly captured through the energy conservation. The mass and the momentum conservation are assumed steady state. So the phase changing material can store large amount of latent heat in a relatively small temperature range. The enthalpy goes through a rapid increase during the melting process. In this case, the enthalpy of the phase change material is calculated using arctangent method because this method describes the enthalpy as a continuous and smooth function, which is favorable to dynamic simulation. Compared to the water heat tank and the phase change material thermal energy storage tank, heat pump system experience much faster transient response to the change and can be treated as a steady state process. So the compressor, evaporator, and the expansion valve are simulated with the steady state model. For compressor, a semi-empirical model is used for predict the compressor performance, specifically for mass flow calculation and power prediction. Also, in this study, the evaporator simulation uses the zoom modeling strategy, which divides the evaporator into two zooms, superheated zoom and two-phase zoom. In each zoom, a lambda model is used. The heat transfer between the refrigerant side and air side is balanced based on the capacity calculated based on refrigeration side and air side. The expansion valve is simulated based on thermodynamic model, which will balance the refrigerant mass flow prediction with the compressor model to converge the system simulation. Finally, a model-based core simulation platform is developed in this study, which is a closed-loop simulation to integrate heat pump system, water tank, phase change material, thermal energy storage tank with the control strategy. This platform can be used to design, develop, and evaluate the system design control strategy before actual implementation and testing on the real system, which allows to quickly detect the control error during the evaluation and the design stage. This platform includes 4 main modules: submission design, control strategy modeling, system submission, and the submission visualization. Submission design is to define a series of submission use cases to automatically examine different control and design strategy according to predefined test requirements. It will generate an input signal to the control module to allow closed-loop submission between control module and the system module. The control strategy modeling defines how the heat pump, water heat, and the thermal energy storage tank should be operated. System submission replicates the physics of the heat pump, water heater, water tank, thermal energy storage tank. Submission results and the visualization is to evaluate the submission results with expected performance targets. The model-based core submission platform was built using Modernica language in Damola software. The Modernica is an object-oriented, equation-based program language, which is very easy to model the physics system. Damola is just a software and the tools to support the Modernica language for modeling and simulating the complex system. So this slide shows how this core submission platform will build in the Damola with Modernica language. So now we will talk about a simple case study. Some of the parameters of the water tank and the phase change thermal energy storage tank are listed in this 2 tables. The water tank is a standard 50-gallon tank with 22 inches of diameter and 63 inches on the head. The PCM thermal energy storage tank is a 6-gallon small tank with multiple 2 centimeter PCM sphere inside. 3 types of PCM material are used in this study. The thermodynamic property are given in this red table, such as the latent heat of melting and the specific heat capacity. So the first submission we are doing is to evaluate the temperature profile inside the water tank at a given water draw schedule. Here we plot 2 temperature profiles, TC1 and TC3, compare the prediction results with the testing data. Overall, the submission agree with the experiment data with reasonable accuracy, but we do find there's a significant error during the short period of time when the water was drawn. Several reasons may contribute this inaccuracy. One important reason we think is because the steady-state submission on the heat pump refrigeration system, also with the quadratic enthalpy assumption. This is the place we will improve in the future. The second submission we are doing is to calculate the UEF, Uniform Energy Factor, use this core submission platform. The UEF is to evaluate the water heat performance with defined water usage. A high UEF means a water heater is more efficient and cost less to operate. We compared a few key performance variables between the submission and the test data. Based on the submission results, there's a 9% difference between the UEF prediction results compared to test data. Also, the tank heat loss coefficient has 10% error. The error of a total water heating energy consumption is small, less than 2%. In the summer, in this study, we developed a core submission platform for heat pump water heater with phase change material thermal energy storage tank. Based on the hybrid modeling approach, use steady-state submission for the refrigeration system side and use dynamic submission for the water heater tanker and the thermal energy storage tanker. And this platform integrates the heat pump water heater with phase change material thermal energy storage submission with control modeling to support the control development and verification. And also we use this submission platform conduct submission to predict the tank temperature distribution, also the UEF calculation to verify the model accuracy. We also identify several improvement opportunity in the future. One is the quadratic enthalpy assumption applied for the heat pump water heater coil in the refrigeration site can generate a calculation error, which we can improve in the future with more accurate profile based on the test data. Another improve we can do is use the dynamic submission for the heat pump system instead of a steady state submission in this case. And the last opportunity we can improve is introduce correction into the heat transfer between the internal nodes inside the tank, which can significantly improve the accuracy of the temperature profile prediction inside the tank. Yeah, that's what we have. Please let us know if you have any question. Thank you.
Thank you, Gian. And thank you to our speakers for their presentations today. And we hope you've enjoyed watching and will enjoy the rest of the Hot Water Forum. Thanks again. This is Harvey signing off.